Welcome to our video lecture on metallic bonding. Our essential understanding for today is that metallic bonds involve a lattice of cations with delocalized electrons. We've used that word lattice before in ionic bonds and in those giant network covalent solids like silicon dioxide. But now we're looking at a lattice of cations, so all positively charged ions, and some delocalized electrons. And we'll talk about that a little bit when we get to our first objective, defining metallic bonding. Our other objectives for today are to compare strengths of metallic bonds. We're going to look at some properties of metals, and then we are going to define what even is an alloy. We're going to talk about how their properties are different from the properties of pure metals. So metallic bonding, what even is happening is our metal atom, so here's a metal atom with its valence electron, atom with electron, atom with valence electron. And what's going to happen is the atoms are going to release those valence electrons, and those valence electrons are just going to flow around the cations willy-nilly. There is no specific pattern, they just flow around and around and around. The result is that we have this lattice of cations, so these cations that form this indefinite structure, and between them we have these delocalized electrons, those valence electrons that have just been released to flow around all of the cations. The negative charge of those electrons and the positive charge of the nuclei, the cations of the metal atoms, sets up that electrostatic attraction. So just like in our other bonds, we have forces of attraction between oppositely charged things. In this instance, the opposites are those cations that are positively charged and those delocalized or free electrons that flow around all those cations. The strength of a metallic bond is going to depend on a couple factors. The first one is how many delocalized electrons are there even? And if I'm comparing potassium and calcium, potassium is going to have a charge of +1 because it loses one valence electron. Calcium is an alkaline earth metal. It has a charge of +2 because it has two valence electrons that are released. More valence electrons, a greater number of delocalized valence electrons, is going to increase the strength of that metallic bond. So calcium's metallic bond is going to be a little bit stronger than is potassium's. Related to that is the charge of the cation. So if I'm looking at potassium that has 19 protons and those couple energy levels, calcium that has 20 protons and its couple energy levels, those 20 protons can pull those electrons in more tightly. And so the radius of calcium is going to be smaller, and then the charge of calcium is going to be greater. The combination of more electrons flowing around, a greater charge, +2 compared to +1, and a smaller cation, the smaller, the stronger, we are going to have this much, much different melting point between potassium and calcium. So potassium's melting point is 63.5 degrees Celsius. Calcium is, oh my goodness, 842. The reason is because, actually the reasons are because calcium has more delocalized electrons. It has a greater charge, +2 instead of +1, and it's also a smaller cation than is potassium. So we're going to look next at sodium compared to potassium instead of calcium compared to potassium. So in this instance, they have pretty much equal numbers of delocalized electrons. Both of these are alkali metals, and so they have a charge of +1 because they release that one valence electron. The charge of these two guys is the same. They are both alkali metals. The only difference is going to be that ionic radius. Sodium has one energy level fewer than does potassium. Because of that, the radius is smaller, and that smaller radius is going to lead to a higher melting point. The melting point of sodium is 97.8 compared to potassium's 63.5. So because these metals have metallic bonding, we're going to have some very specific properties that result. The first property is electrical conductivity. So electricity is simply moving electrons. If I can get electrons to move, then we have some electrical conductivity. And so what happens is these electrons can just flow along the copper wire. I can set up a charge where I've got something negative here. The electrons are going to be repelled by that negative something on this side. And then I'm going to put a positive charge on the other thing. Perhaps these are batteries or something like that. And the electrons will be attracted to the positive, move away from the negative, and that movement of electrons, those flowing electrons, is electricity. This is similar but a little bit different. We're showing that that electron can move from one atom to the next, and that movement of electrons from one atom to the next is electrical conductivity. Metals are also malleable. Malleable means that they can be hammered or dented, molded. I can smush them up a little bit, and the reason is this. So our cations of metal atoms are here, and we've got those electrons that are flowing around like this. If I put a little bit of a stressor, then what happens is these layers of metal cations can kind of roll over each other. They can just shift all around. And this is because those electrons act almost like little layers of grease in between those cations. Nothing is stuck in super specific hard bonds. Instead, they're just like attracted to these clouds of moving things, and that allows for metals to be malleable. Those electrons moving is also going to result in the luster of metals. So light shining on these pieces of metal with these electrons moving all the way all around, that light is going to kind of disperse a little bit. That photoelectric effect makes metals shiny. So we have these other things called alloys, and alloys are homogeneous mixtures of metals. They're not exactly compounds because they don't always have the same ratio of different metals in the alloy, and so we call them mixtures, not compounds. So alloys are homogeneous mixtures of metals. Sometimes we actually throw in a non-metal like carbon. And we're going to name the alloy after its major element, and then we're going to have whatever comes next will be the alloying element. Sometimes we give our alloys special names like brass. Brass is mostly copper with a little bit of zinc. Steel is mostly iron with a little bit of carbon, interestingly, and then sometimes some other stuff. Alloys tend to have slightly different properties from pure metals, and the reason is because they are those homogeneous mixtures. Alloys tend to be stronger, they're less malleable, they're also more resistant to corrosion or rusting, and that's because of those different sizes of cations. So maybe this is our zinc and this is our copper. And what's going to happen is, instead of having this lovely layer of symmetrical cations that can slide over each other, like we talked about on that metals slide, instead, now we have these chunks that kind of get stuck on each other. So these guys are trying to slip and slide past, but he's just too big. And so that irregularity of the cation sizes makes these guys less malleable, a little bit stronger, and often more useful because they are stronger, and it also makes them less resistant, more resistant to corrosion. And my friends, we did it. Good work. See you in class.